So I'm happy to introduce Mayur Thakur. We are from the same undergrad college, IIT Delhi. He did his PhD at University of Rochester and is right now an assistant professor in University of Missouri, Rolla. His research interests are in network and graph algorithms, combinatorial optimization, time series analysis, simulation and modeling, and complexity theory, which is dear to the hearts of many of us here. He's also held positions at Northeastern University, Alamos Labs, Equinox Corporation, MSR, Philips, and so on. So I'll look to my
What was that list again?
The city.
What was the list again?
Northeastern University, Los Alamos Corporation, Los Alamos Labs, Equinox Corporation, MSR.
Yeah, these are all some short-term positions.
Yeah.
All right, we'll talk about net and the city.
Hey, thanks Gagan for the introduction. It's nice to be here. First time in California actually, so this is very strange because I've been in the US for 8 years now. Okay, the talk is going to be on net and the city. This is ongoing work with collaborators at Virginia Tech, Northeastern, and Los Alamos actually. I am going to first motivate why we want to look at city nets, what those are, and then basically describe how we build our model of city nets. Then I'll present some analysis and what the structure of the city net looks like. And then at the end, I'll present some analysis on attacks that we have. Okay, so upfront, let me describe what city nets is, define what city nets are. There's no. Oh, I see. Yeah, I see. Yeah, sorry about that. Okay. All right. So when I refer to a city net, what I mean is exactly this. I mean a set of routers, end hosts, and links that are located in a particular metropolitan area. So think of New York and think of its boundaries. Well, it's not defined well, but let's say I define the boundary for you. And then think of every router, end host, and link that is located inside of that boundary. That's what I mean by the city net. Okay, the connection there. That's what I mean by a city net. So what we want to do is to uncover the structure for large metropolitan areas like New York City, like Chicago, and we actually have done that. The reason for doing that is the following. A lot of study has gone into, a lot of people have studied the general structure, the internet at large structure. And also there has been a lot of study in the relevant sub-networks. For example, ISP structure has been studied, autonomous system structure has been studied. What we are doing is looking at the local structure, the geographically local structure of the internet. Why do we want to do that? Well, the internet as an infrastructure has grown with humans, and humans have grown the most in cities. So what we want to do is look at how the infrastructure has grown in dense areas, dense both with respect to human population, and in terms of importance, because cities are where the businesses are, cities are where the universities are, cities are where most of the people are. In terms of computer networks, what this will do is facilitate network simulation studies. You'll see some aspects of it where we study the vulnerability or the robustness of networks. What we want to do is to develop a methodology that anyone having access to a few nodes and stuff can create a structure, can create a map of city nets, and then use that for simulations. We plan to release models for the research community. So from what it will come out of this research, we want to package it and release it to the network community, because the structure, the knowledge of city nets, the structure of the city is not known. Okay, one thing that I wanted, yes.
You mean models or data? Exactly what do you plan to do?
We can't release all the data because some of the data is sensitive. Okay. So what we'll do is we'll anonymize and release it. Is that what you're asking?
Both. Is it a mathematical model or is it
we have it's actually data from real world, but we also plan to do research and from that real world data make mathematical models. Okay, both. But we can't release all data that we have because some of it is actually sensitive, and but we can anonymize and release. So even real data we can anonymize and release. So for example, not have any IP addresses, just give them integers. All right, that would. Okay, one important distinction between our model, I'll describe the model, but before I start, our model of city nets or networks in general for now, but let's go with the city nets, is a path view. So we don't look at a network as a graph, which is what typically you would think. What we look at a network, when I say city nets, a model of a city net, I mean a set of nodes and a set of paths on that nodes, on those nodes. And then you can think of attaching traffic weights and stuff on that. But this is the crucial difference. It's paths as opposed to, it's a path view as opposed to a graph view. Now, why do we want to do that? This basically two reasons. Routing on the internet is policy based. Just because there is a path on the internet doesn't mean any packet will travel on that path. So we believe that the path view is the more correct view. All right. Also, it has been shown that the paths on the internet have this dominant paths phenomena, where at steady state, all traffic between this point and some other point is dominated by a single path, even though there are multiple paths that could go. It's changing slightly because of new technology and stuff, but still, the internet shows dominant paths. So again, when I say a city net, what I mean, or a model of a city net, what I mean is a set of nodes and a set of paths over those nodes. So I'll describe all that in a later slide, but roughly speaking, this is the boundary of the city. These are nodes right outside the city. So that's what I call the border nodes B. These are the set of routers, also called internal nodes. So these route traffic, and these are a set of destinations or end hosts. Okay, that's the basic model. Okay, what this shows here is that you have a small cut, but we'll come to that. But the basic idea is path instead of graph.
You're thinking only of physical nodes, not wireless.
No, at this point it's just, and also you can think of what level is it level 2, level 3? We are looking at the IP level, router level. Okay, people have done work at the AS level. So what is the AS level connectivity? Okay, or people have done at even lower levels. For example, what's the physical connectivity? We are looking at the IP level. Okay.
Are you going to get to it later, or is it a good time to ask about the length of the paths, typical length of the paths?
I'm going to get to that. Good question, but yeah. So length is the two, is the unweighted length and the weighted length. Weight is hard, so we have not done that. We have some models, but weight is basically traffic or capacity, and it's hard, but we have some models for that. I'll come to that. So the problem statement is we want to design a robust methodology. Here, the idea is, in addition to the data, we want to develop a methodology for inferring realistic path network views of city nets. Okay, what do I mean? I've described what path view is. What do I mean by realistic? What I mean by realistic is, first of all, it should be defined. It should be inferred from real data. And secondly, even though it's impossible to have all routers, there's just too many of them, and all end hosts in your model, it should be realistic from a point of view of whatever metrics you're interested in. Or whatever metrics common simulation studies are interested in, the model should have those properties. The model for those metrics should satisfy the property of the real world. So our view, as I just mentioned earlier, is the router level view, where each node, think of it as a router or an end host. Not in a lot of different studies, each node is an autonomous system, or you can think of each node as an ISP, or you can think of each node as a so this, when I say the router, I mean an IP router at the IP level, not at the physical level. Okay, because logical connectivity could be different from physical connectivity. There has been work, in particular work by Brightbot, and I think someone at Google actually, at the physical connectivity, but we are not doing that. Another thing that we are not interested in, and that is from this, is we are not interested in the transit traffic. If you see, all paths start from outside and end inside. There could be a path that starts from outside, goes inside, and comes out. We are not interested in that. We will not model that. Why? Because we are interested in how the city is connected to the outside world and vice versa. How the outside world is connected to the city. So we are ignoring transit paths. Okay. Other thing is, we actually are interested in forward connectivity and backward connectivity. However, 50% of the paths have been shown to be symmetric, and because of the way we do, namely trace routes, backward connectivity is harder to do. So even though I'm claiming I will be sort of implying that it holds for both forward and backward. Actually, I'm going to caveat it by saying that it's only forward paths. Okay? But if you ask me to hazard a guess, I would say that the forward and backward would not be much qualitatively different. Okay? But our models are not based on backward paths at all. It's just forward paths. Obviously, the issue here is that path from here to here path from A to B might be much different from path from B to A. But typically, it's 50% of the paths are in fact actually symmetric, and a lot more share many other properties. Okay, so some related work. This is a ton of activity. I'm missing a lot of stuff here, but I'm just want to give you a flavor of the kind of work that has been done. Different views of the internet have been looked at. So the router level view, and this is for the general internet. Ours is only for the cities. So there's router level view. You have the autonomous system view or the ISP view. Okay. Also, related to our work, in fact, a very crucial part of our work is knowing which IP address falls in which city. So we are using work that other people have done on geolocation. Given an IP address, how do you locate where? What is the geography? What is the latitude and longitude of that? People use different kinds of triangulation techniques, both in open research community, and there are whole companies, and we are using some data from these companies, even though we could, in principle, do all of their work and then use that data, but we are not. We are using it as a black box. Geographic properties of routing have. Sorry?
Whose data did you use?
Yeah, I'll come to that, but it's Akamai, Digital and Envoy, Cova. So you use 3 sources, and they are all into all this. Geographic properties of routing. So if a packet has to be sent from Mountain View to New York, how does it travel geographically? Does it go to Chicago first? That has been studied. It has been shown that it's not optimal, but a lot of times it's optimal in terms of distance. This is ours. We look upon our work as a part of the bigger study of understanding the internet and how it has grown, which has there's a ton of work in that. In particular, I note this is the first work that introduced that hinted that the internet graphs or internet has this power law structure where you have, which is the reason for efficient routing, but also leads to vulnerability. So that's where we look upon our work as a part of the bigger internet visual tomography. There's a typo there. We are not doing any visualization though. And again, even beyond internet, there's work on complex networks, so social networks, internet, so on and so forth. Power networks, so electrical power networks. I've done some work that is related, but it's not part of this talk. Okay, so what is the basic methodology that we have? So our goal again is to find a path model. So I want to give you a set of nodes and a set of paths over those nodes. For a given city. So let's assume a city like Chicago, for example. Chicago is, if you have a specific city in this talk, I'll show Chicago's example. Okay, so I want to give you that. I want to give you a path model for Chicago. So how do we do it? The first thing we do is find the set of all IP addresses that lie within Chicago. Okay, this we do using data sets. So we are actually not doing research in here. We're just using other people's research. Now, after that, what we do is we sample. Since we can't run trace routes, our basic methodology is trace route. Since we can't run trace routes to all of them, we sample intelligently so that per trace route, the number of nodes and edges discovered is improved. Okay? Then we actually trace out from a lot of different vantage points, close to 44 vantage points, to every IP in that set that we have, in that sample set that we have. We clean data, and then we build a path-based model. We call it the BID model, and you sort of saw the glimpse of it, and I'll come back to it. But essentially, that's what we do. You have a sample set inside a city, and you have all these sources. You run trace out from all these sources to this sample set, and you get your path-based model. And we do analysis after that. Okay, so the first step was basically the IP to geographic mapping. This, as I mentioned in an earlier slide, it's an active area of research. We are not doing research in this. We just take data from, this is actually proprietary data, but if we really wanted, we could spend effort into and build our own system. People have done that in the research community as well. So these are all well-known leaders in their field. What we do is take these three data. The data doesn't match because of obvious reasons. It's not exact. We don't know where the city ends and the suburb starts. One thing we want to note is that we want to consider the metropolitan area because we don't want to lose out on home customers, for example, blocks related to home customers. That's just one. So we want to look at not just downtown, but the metropolitan area as well. Again, that definition is also not clear. But basically, what these data give us is for each IP, it gives us it gives us a name, which is basically the name of the city. Actually, they do it by blocks. But then you have to merge these data. How do you merge these data to get one clean data? Okay, the basic method that we have, the basic tool that we have, as have other studies done, is trace routes. What trace route is basically you start from a point, it gives you the route from that point to any other point in the internet. Okay, so this is an example of an actual trace route from our data set. So you wanted to find out the path, the forward path to this IP address, and this gives you that. We are not using the time information, but you could use time information for waiting, for example. But we're not doing that as of now. This is basically an internal bookkeeping that we have. Okay, so the trace route is a utility that's been used a lot in network studies. It uses the time to live attribute of IP packets. What you do is you say, okay, the IP packet should expire in, say, 5 steps. So at the 5th hop, it expires, and then just by the way the protocols work, hopefully the router will send you a message saying, oh, your packet expired. So you know what the 5th router is, essentially. They're not required to send it, but that's why trace routes a lot of the times are not successful. In fact, the success rate is only about 10% or so. Okay, but that's what we have to live with. So what we have is, yeah. No, that's fine.
From the trace routes, I seem to remember there's 2 different ways of doing it with ICMP and UDP.
Yeah, we do. Okay, I don't mention that, but we do all sorts of optimization, which is the point of this slide actually. There's lots of different ways to do it. We choose ICMP because UDP raises more flags. So what you have to be careful about trace routes is that, first of all, they can take a long time. So if without our optimization, which I'm not mentioning here, so 100,000 trace routes, which is a typical number for a city, will take about 2 to 6 weeks. Okay, depends on how many successes you have had. We do trace routes. For example, we don't send 3 packets, which is normally what they do. Remember, we're not interested in very fine structure because it's not possible to get all the. It's more important to get more structure than to get every single small one of them. So we do these optimizations. Part of that is using ICMP packets. Okay, and then we reduce it to a reasonable number. It's like 1 day for 100,000 trace routes, essentially. So the utility that we have is basically a utility for collecting trace routes, and it has tunable options, including that. But the way we do it is always use ICMP. It works across machines because other machines, because sources in different locations have different operating systems. It does have error recovery. So if you stop it at a certain point, you can start it up without losing much data at all. So I'm not going to go into the optimization, but some effort was spent there in trying to make sure that this was reasonable, because this is just not reasonable. Okay, so what we did was we chose 12 of the 25 largest cities in terms of population within the US. And we chose cities such that they were distributed across the US. It just so happens that there's no big city here. Otherwise, you see that it's sort of well distributed. So you have stuff there, stuff here, stuff there, and stuff here. Okay, so there are 12 cities in our study. So the reason for looking at multiple studies is because we also want to look at across city similarities or differences. Okay, so that's the destination cities, and that's the cities in our study. The data that we use are the following, the data sets that we use. We have Skitter, which is basically Kaida's net measurement tool. And the data that we used, this is not all the data that we have, but the data that we used had trace routes from 20 vantage points. What Skitter does is basically it has a set of IP addresses that periodically it trace routes to. And some of that were useful for us, so we took that. All right, so not all of data is used here, but we took that. But they use 20 vantage points. Planet Lab is just a network of computers. You can get slices on it. We use 14 such vantage points across the world, but most of them in the US, and we traced out to our data. And in addition, we used our vantage points, 10 in numbers. Basically, we asked our friends, can you lend us a computer for 7 days, 10 days, whatever, and we'll run trace out from that. Okay, so overall, it's 44 vantage points. One crucial thing is that recent studies have shown that if you do not trace out from, if you don't run these trace out based studies from multiple vantage points, lots of vantage points, you could get misleading results. Okay, so that's why a lot of effort was spent in that. One obvious thing to consider was, and we did, was rocket fuel, which basically maps autonomous systems, or actually ISPs. Okay, so they have mapped, for example, Verizon. However, when you look at that data, the amount of data we could use wasn't enough because they're using very few trace outs. So we decided not to use them. Just to give you an idea of the amount of data that we have per city, and Chicago in particular, so bigger cities have more data, that's why Chicago is almost twice the average, is about 850,000 trace outs that for an average city, of which I said that not all trace outs complete. Only about 100,000 trace routes did complete. However, we don't just throw away all non-completed trace routes. The amount of trace routes we use, the number of trace routes we use for an average city is about 200,000. So that's a lot of data. For Chicago, it's about it's more than 500,000. Okay. The first step I said was to find a set of IP addresses to which to so that we could trace out to that. Now, one thing we found was if we just randomly sample, a lot of IP address space is just wasteful. It's just not used at all. If you randomly sample, is that good, or do you need some other sampling? What we found out is that we actually need some other sampling. So what we did was the following. Let me describe the result, and then I'll say how we did it. What we did was we took the IP address space, IP addresses within a city, and then we broke it up into blocks, and I'll describe how the blocks were made. And then what this shows is the number of IP addresses versus population, and it shows the number of blocks versus population. And you can see a much better correlation with the number of blocks than with the number of IP addresses. What does it tell us? Basically, what it tells us is that the number of blocks is a closer description of the complexity of a city net than a number of IP addresses. So what we did is we did block sampling. Instead of sampling randomly from IP addresses, we had these blocks, and then we sampled uniformly randomly from those blocks. And again, you might ask, well, it's just correlated with the population. How do you know that it gives you more complexity? To tell you the truth, we don't. However, if you look at the performance in terms of discovering elements of city nets, nodes and edges, forget what this is written here. What we see is that if you do this uniformly randomly sample from IP addresses and versus our block sampling, we get 120% improvement. Okay, what this means is for us for the same number of trace routes. So if you do 10,000 trace routes with uniform sampling versus block sampling, ours is 120% better across all types of nodes and edges that we looked at. So this is tiny. Forget that. This is interior nodes. So these are connections between routers inside Chicago. These are total number of edges. These are I to D edges, means these are connections between routers and end hosts. Okay. So across every metric that we looked at, we got a huge improvement, which tells us that it is at least much better than the most trivial way. There could be better approaches for sampling. What we did for the sampling part was we took the data that we have and from the geo sources, and the data already has some. So the idea there was to get to cluster. So this is basically a clustering problem. We want to cluster IP addresses such that all IP addresses that have similar routing behavior are clustered in one. Because if you do trace out to one of them, you know the result for the others as well. Okay. The geolocation data that we had already had some block information. In fact, the BGP, for example, when you do this routing, it already has this block information. But we still had the problem of not aggregating too much, because if you aggregate too much, then you lose the information, because remember what we would be doing is doing block sampling here. So we had to find a nice middle ground. Okay, so that's what we did for the block sampling part. I've sort of described this BID model, but just to formally state what the BID model is, we have a set of nodes, and they are divided into 3 sets, partitioned into 3 sets. The border nodes are nodes that are just outside of the city. The interior nodes represent the routers inside the city. The destination nodes represent the end hosts within the city. Okay, so this is just every path that we have starts at a border node, ends at a destination node, and must have at least one router here. Okay, only some paths we found didn't have this structure, but most paths do conform in the real world, do conform to this structure. Okay, so note that we are ignoring what happens beyond this, because we are interested in interested in looking at the connectivity of the city to the outside world, or vice versa. Okay, that's why.
Estimating how much of the data is obfuscated from you by NAT? There are lots of little subnets in my house, for example, where you can't tell what's inside because of NAT.
And all those are difficulties now.
And so you sort of expect that lots of endpoints would be like that with small numbers. But I'm curious if there are any big numbers that are hidden from view, like major subnets in corporations or ISPs.
If you had to ask me, I would say yes, it's a possibility. But if you ask me for an estimate, I would not know that. We can only know. One thing we did do was not throw away incompleted trace routes. So even if you have those, you would probably get incomplete paths that just, after that point, they just give up. They can't go beyond. So what we did was we didn't throw them away. We did the best we could do, sort of attach a dummy node there. So we don't know which nodes correspond to, if Microsoft has a server blocking everything. We don't know which destination node corresponds to that, but there's something that possibly corresponds to that. Okay? So, and if it's a big chunk, it will have higher weight. We'll see that later on. But yeah, I mean, that's the obvious problem. There's so many things that are hidden, and that is any trace route study will have this problem, essentially. You could do some. Okay, I should mention that there's some other optimizations that we didn't do that we could do. For example, people do source routing. Okay, when you ask to forward a packet from here to here via this node, for example, we didn't do that. That could increase the amount of nodes we see. However, we're trace routing with so many places. If you ask me to guess, I don't think it would matter in our case. I would also mention that typical trace route studies are not done from these many sources except rocket fuel. But rocket fuel was trace routing to a small set. Again, the border nodes connect city nets to the outside world. The interior nodes are routers inside the city, and destination nodes are end hosts. And we are only interested in outside to inside traffic. Okay, so and again, what we did was we have the trace routes, and we want to go to the BID model. What we do is just cut it right at the border, essentially. Okay. Also, some optimization. We only keep trace routes that at least go 2 hops into the city. That will, otherwise, you can get a path that has one B node followed by a destination node. We didn't want to do that. We didn't lose too many nodes because of that, though. For now, we still have the problem of, if I give you a path, I haven't labeled it as an interior or a destination node. Okay, because what can happen is this node is a destination node in one, and it is a non-destination node. It's an interior node in the other. But it's a fairly easy thing to, if you think about it. Suppose X is a node. Okay, in all our traces that we have. A border trace is simply a trace that is cut at the border. So X is a node, and if we have ever seen it being forwarding a packet, we know that it's a router, because end hosts will not forward packets typically. So we label it as an I node. On the other hand, if it's a dead end, which means that it's the last node on an unfinished trace route. What that means is that someone in the internet thought that it could forward a packet, right? And assuming that someone was right, it's probably a router. So we label it as an I node. Everything else we label as a destination node. Okay, so that's our simple heuristic. Again, there is inaccuracies in all these steps, but that's just the nature of the game. However, because of all this inaccuracy, data validation becomes an important step. So the steps that we did take to validate our data, we asked the following question: is our data enough? Have our models converged? So we did some statistical tests for convergence, and I'll describe 2 of them as follows. So let's look at how many new network elements we are discovering per trace route. Actually, it's not per trace route, but it's per source. So what we did was, for one city, in this case, we took all the trace routes that we have, divided them randomly into 10 buckets, and see, okay, what is the return for this one? And you can see that it's at that point it's very insignificant. Okay, so that gives us that it's at least as far as trace route studies are concerned, we are converging. The other one that is sort of non-standard, this is standard. The other one that is sort of non-standard is the factorial test, which we basically are asking the following question. Here it was just a simple number of nodes, number of elements, number of edges. Here the question is not that. Here the question is, look at the in-degree distribution, let's say in this plot. Look at the in-degree distribution, and is that curve, is that metric converging? So what this plot shows is, this is the solid line is the in-degree for 4 sources, okay, for a particular city. I think it's Chicago. For a particular source, just for 4 sources. And these, the dots here, above and below, are 2 standard deviations above and below for 3 sources. So think of 3 sources and the plot that you get. And now go to 4 sources and the plot that you get. And what this shows is that within a band, and what this shows is that the 4 sources is between 2 standard deviations above and below the 3 sources. Okay, so even with 3 sources, or 4 sources that is, we are sort of converging. Okay, the standard deviations here, for example, are really, really small compared to the mean. Okay, each point here, by the way, has been, each point here represents multiple runs. Okay, so the way you compute this point is, that's the reason it's called a factorial test, is you choose, so you take your set of sources, you take your set of destinations, divide them into sets, divide them into sets here, and then take subsets. Okay, and you take lots of subsets so that you get statistically significant results. Okay, similarly for the out degree, again, in fact in this case only 1 standard deviation above and below, it's still converging. Okay, so this gives us confidence that at least as far as we could do in using this methodology, our results have to be believed or can be believed. Any questions so far before I go on to the results section? Okay, so now that we have constructed these models for city nets, so again our model is set of nodes and paths that have been derived from actual trace route experiments from 44 different sources. Okay, what can I say about the structure of city nets? How are they different from the internet at large? And one question that we are asking here is about the robustness. I'm going to describe a little bit of all of them. As expected, the number of nodes increases linearly with the number of blocks in the city, sort of linearly. It's well correlated. Okay, so this is just that. I'm sorry if these are really small, but this is the number of border nodes. This is the number of interior nodes. So this is the B, I, and this is the number of destination nodes. Okay. Again, the correlation with number of IP addresses is not that good at all. This is much better than the number of correlation with IP addresses. One interesting thing is, I think you asked about the depth, the length of these paths. The length of these paths are pretty. They lie in a pretty small range. So most of the paths, note that there are no paths less than 2 because we are imposing this structure that you must have at least one interior node, actually 3, because I'm counting the number of hops, the number of nodes. Okay, so between 3 and about 6, that's the number of hops for almost 99% of the paths. Okay, and the different plots are for different cities. Okay, so there's one curve per city here. All right, there are not 12 of them because we choose 5 or 6 or 7 of them for that. But essentially, one way to think about this is the following: if there are lots of paths with lots of long paths, what does it tell us? Maybe one way to think about this is that there is some ISP that is not doing a good job. essentially, because then that ISP, if you are a customer for that ISP, you have a long path. Okay, then people will probably shift from that ISP to something that performs better. So this is the paths are the lengths are not that different. They are okay. So now let's look at one difference between the internet at large and the graph view and the path view. This is the total degree of edges here, and this is the total degree ranks. What I mean by total degree of edges is the following. You take an edge and you take the sum of degrees of one side and add it to the sum of degrees of the other node. Okay, that's what I mean by total degree. Oh, sorry. This is not that. This is just for the nodes. This is the total degree for the nodes, which means the total in degree, the sum of the in degree and the out degree. Okay, that plot is coming later on. So now you see that as observed earlier as well. This is not just for the first time it has been observed, and this is log plot. So this is roughly a straight line again for different cities. So it's a power law. However, if you go to the path degree, so number of paths going through a particular node, okay, and this holds for nodes and edges as well. It's definitely qualitatively different because you see this hump here.
What is path degree?
Oh, the path degree is the number of paths going through a node. This is the number of edges. So the path degree is way different because, and in particular, what is happening is that there are fewer larger nodes, right? Because the mass is distributed towards the smaller nodes, okay? And we'll see a consequence of that. In essence, what you have is that you have smaller cuts in city nets, even fractionally, because you have smaller number of large nodes, right? Because the mass in the tail is small as compared to, for example, the total degree. Okay? So the in degree, out degree, and the total degree distributions are power laws. I only showed you the total degree distribution. In case I didn't explain this, what this is basically you arrange the nodes in decreasing order of their path degree, and you plot that or the log of that versus the path degree. And it is well known that for the internet it's a power law. So that's why you see a almost linear relation here. Yes.
So people suggested a model for this creation of the power law, this copy-paste model.
Yes.
I was wondering if there are any ideas of such models for the distribution of the path degrees that you see.
We don't have them, but that's one area that we are, with future research is what we want to come up with. For example, they have the rich gets richer model. We want to come up with something that has, but this is definitely less heavy-tailed than power law. Okay, so yeah, it's something that we have thought about, but I don't have a result to show you.
Did you try fitting it to other close cousins of power law, like the log normal?
Log normal we have not, but that's again, this is stuff in the future. However, at this point, it's more qualitative than quantitative for reasons that I'll also explain later on. But yeah, that's again something that we would want to do is to fit to some of these curves. One problem, but so much is clear that it's qualitatively way different. And we'll see some consequence of that shortly. Next few slides. And something you would have already guessed, I know why this is taking so long. There's lots of points, this is a scatter plot. Okay, so now let's look at whether, if you look at an edge or a node and look at its degree, is that a good indication of the number of paths going through it? And the answer is no, actually, because if you look at the total edge degree, and this is the edge path degree, what this means is the total edge degree is the sum of the degrees of, so consider an edge uv, the total edge degree of E is just the degree of U plus the degree of V. Okay? So, and the path degree of an edge is just the number of paths going through it. Okay? So what this means is just because an edge has lots of connections doesn't mean a lot of paths are going through it. Okay? It might be true for someone, but it's not necessarily true. You could have an edge that has only a few neighbors, yet you have a lot of paths going through it. Okay? So that's what this means, because there's just no strong correlation at all. And you can replace this with total node degree and still it's qualitatively the same.
Do you have a final picture of that based on whether the edge is B to I or I to I or any other?
I might, but not in this presentation. I might. We have lots of, I want to finish on time. I'm already over time. Okay. one thing, okay, so this is just uncovering different structures. I know it's a bit unstructured for that. But again, another property that we have is, let's do some definitions. When I say last router, it means the inode, the router, immediately preceding the destination. Okay? And when we say a block, when we think of a block of IP address, which we say it's homogeneous if all paths to all nodes in that block have the same last router, which basically means that a block is homogeneous if basically, as far as routing is concerned, it's the same route from everywhere. Okay? Finding this is not trivial, but you can randomly sample and find it, and we did do that. A cluster router is basically a last router that serves a homogeneous block. Okay? So what we have found is that cities have a lot of cluster routers. So 55% of Austin, for example, of Austin routers are cluster routers. And the number is higher it's roughly in that range. So what that means is that the last hop router corresponds, as a fraction of the total number of routers, the cluster routers are significant. Also, that pretty much means that the number of homogeneous blocks is significant. So lots and lots of blocks, a lot of the blocks are homogeneous, which also lends credibility to, first of all, our block sampling, because we basically need one path for each block, but also uncovers a structure that we like to call as the apartment hypothesis. Maybe what is happening is you have these apartments where lots of people live. And again, this is an analogy I'm giving you. And then they are served by a common router. And basically what the ISP is doing is bringing a path to that. And then from there, you have connections to all of that. All right? As you see, almost 80% of pretty much every city is homogeneous. City blocks is homogeneous. Again, this was found experimentally. Just a short note on the robustness analysis. And this is a consequence of the path distribution being less heavy tail. What we did was, we took the city nets, and the question we asked is, how many nodes do I need to delete so that 80% of the traffic roughly is deleted? We did it for two things. One is the number of paths, and the other is block uniform weighting, where each block is assigned a weight of 1, a traffic weight of 1, and then it is distributed equally to all the paths coming into that block. Okay? And the results are pretty similar. Okay? That's why I'm showing only one. So the topmost one is when I do a target node. So I know all information about all the paths, and I'm trying to delete the one that gives me the most. So it's like a set cover heuristic, essentially. And these are just heuristics because it's NP complete to find out. Okay? So I do using the target node. So I'm using the number of paths going through a node as the heuristic. This is the number of paths going through an edge as the heuristic. This is the number of, and this is the in degree of a node is the heuristic. So you see that if you use the in degree, since it's not that well correlated with the number of paths, there's a significant gap. There's only 40% roughly, 50% roughly. This is close to 80%. Okay? So think of an attacker, if you're just looking at the graph view, okay, you are probably not going to do as well for the attacker as if you were looking at the path view. Again, it argues for the path view. These are just random, just for comparison. You just pick nodes randomly, and the internet, because of the power law structure, is known to be resilient in that case.
Sorry, just so I understand. By target, you mean adversarially chosen?
Yes.
Okay.
Yes.
And that's a factor of 10 to the negative 3 there?
Yes. Oh, yeah. This is, so a good point. That's my punchline.
Half a percent at the end.
This is 0.5%, and it deletes 80% of the traffic. Okay? For the internet, if you look at the Fuller's graphs and stuff like that, this is order of magnitude larger. So you have still the same curve, except you might have to, I forget the exact number, but it's at least 1 order of magnitude larger. Okay?
The geographic distribution of nodes and how it would be impacted. So I know there's a couple buildings in downtown San Jose that if you park the truck bomb outside them, you can range it in.
Now, see, that is very hard to do. That's the first idea we have. We are going to plot it. The problem is the way geolocation works. The granularity is not that much, so it will give you, okay, it's within 10 miles or so. Okay.
So you didn't have more accurate information.
No,
for any of these
no,
nodes.
and no one has, to my knowledge. But that's an interesting thing to do, because if you can do that, we can do quite a few things. Yeah, we didn't have that. All we knew was that this is in the city and this is outside the city.
Okay. We used to be able to sever the East Coast from the West Coast for civilian voice traffic by only cutting 4 places.
Wow.
In the
I
U.S.
didn't know that.
Yeah, that was in the early 90s. They fixed it.
Okay, just some more definitions. Again, looking at the vulnerability structure, when we say the waste of a city, so the structure that we have is sort of goes in, is sort of, there are few paths coming in or few edges coming in, and it branches out, okay? And then think of it as you're going to have highways coming in, and then when you go to your home, it sort of branches out into small streets. Okay, that's the mental model that I have. So the waste of a city, so this is what we call the waste, and then you have the hip there, and then the waste of the city is just the smallest number of routers that carry 80% of the traffic. Okay, the hip of a city is the smallest number of end hosts that account for 80% of the traffic. Okay, and what we have is basically a small waste, large hip structure. Again, this is the uniform block weighting that I mentioned earlier as well. It's not important. The results are pretty consistent, actually, even without that. So just to give you an idea of the waste to hip, these are not fractions. These are percent. This is 0.5%, essentially. Really, really small, except for a few. And these are, if you look at it, these are small cities. So what is happening is there are 2 things happening. There are fewer number of hosts here compared to the number of routers, and there's also I'm figuring there's also some error that we have. Related to that, we have what we call a dosimeter index for it's basically denial of service attack meter, which basically say, okay, if adversarially chosen, you delete k nodes. Okay, k is fixed at 10 nodes. If the adversary, where will it impact the most? So think of it as how many people is it going to impact. So it's the ratio of the population to the waste, essentially, because remember, waste is 80% of number of routers that carry 80% of the traffic. Okay, and we see that there is a correlation between the size and the population and the size and the dosimeter here. So where larger cities have smaller doses. Small is bad because it means that it is population. So these are larger cities. And small is good, large is bad. Large is bad, which means that with a few nodes, you can disrupt a lot of population. But larger cities are actually worse. Okay, because it's a downtrend here. This is an outlier. I think it was Washington or so. However, note that all of this is a related one that you might think of is the ratio of the incoming to the outgoing in a certain sense. So the ratio of I to D edges to B to I edges. Okay, so we are claiming that this is much larger than this. Okay, these are sort of similar ones. Again, this represents the degree of disaggregation when the paths come into the city. Anyway, one interesting thing that we got is that this is not. I mean, this is from the data. We're plotting the actual data. So that is very surprising. But what we found is that if you look at the in degree, out degree, and total distribution for these values, actually you can have for these values you can actually prove that the edge skew, which is the ratio of I to D to the B to I edges, so ratio of your branch streets, your local streets to the highways. Okay, so that ratio is actually for these values log n, which is not which is why this is a straight line, because this is this is a log scale. Okay, so this you can prove. It's not that non-trivial. It's pretty trivial to prove, actually. Okay, so I was going to talk a little bit about this theoretical part of our work, but I'll just end with the one result that we have. So we have shown that city nets are vulnerable in certain restricted sense. Note that we don't have traffic, so we're only looking at what we have. So the obvious question is, can you detect large-scale attacks? So just defining one reasonable large-scale attack is the following. We say that an attack is k epsilon attack on a path network P if the adversary can remove up to k nodes or edges, k network elements, and he must cause a disruption to at least an epsilon fraction. So if it is 10 and 0.2, by removing 10 edges, you must disrupt at least 20% of the traffic of the paths. Okay, so this is the kind of attacks that we have been looking at. It's inspired from work by Kleinberg, who looked at the same thing for graphs, not for paths. Okay, so one application might be that you install monitors on chosen endpoints, a small number of monitors, so that any large-scale disruption shows up. Okay. So what we can prove is that for every path network and for each k and epsilon, there exists detection sets of size that are polynomial in k and epsilon, inverse of epsilon, as independent of the size of the path network, so independent of the number of nodes and independent of the number of edges. And in fact, you can have a simple randomized algorithm that can do that. It's based on VC dimension and a very strong result by Hausler and Welzel, which I'm not going to define, but that was the proof there. But basically what we get is that the VC dimension of a set system that we define, again, I'm not defining that, what VC dimension is for lack of time, but we get that the VC dimension of a set system, a relevant set system that we define is k log c. And Hausler and Welzel gives us that it's polynomial in this and epsilon prime. So what you have is that it scales up very well with your path network. It doesn't depend on the size of the path network only at all. It only depends on your k and epsilon. One crucial thing that we need to know is that what is the C? I didn't define what the C is. There's a technical condition that we need to have in our path network, which is the following. Think of two paths. They merge and they deviate and they merge again. C bounds the number of times they can do that. So it can't be arbitrary. It can't depend on n. Otherwise, we don't have our result. So that's the confluence coefficient. However, because internet paths are destination based, we have found that you never see more than 3 confluence. Okay? So once you have that, you have small detection sets. Just to conclude, we have studied city nets as important subnetworks of the internet. Crucial difference between our and other work is that we have a path view and we have a methodology to make realistic maps of city nets. We have taken pains to ensure the statistical validity as much as we can. The cities have show structures that is different from the structure of the internet at large, in particular the small base large heap structure, and they seem more vulnerable, an order of magnitude more vulnerable than internet at large. Okay? So if you want to attack a smaller portion, you can do it easily. In terms of fractional as well, right? Remember the detection sets are fractional. Okay, so that's where my talk ends. Sorry for going over time. Any questions I would be ready to take.